Right. Hi, everybody, or shall I say, Chucky Nyaki, everybody. Today I'm going to talk about asynchronous programming. And what I want to promise to you is after this talk, you'll be able to write concurrent code under this paradigm much more effectively, thanks to a better intuition about it. Like, this will help you discuss it more confidently, write it correctly in either interviews or in the actual job, and it will help you decide whether to actually use it. So in other words, it's just profit, profit, and profit. Does that sound like a good idea? All right, so, but first, has anyone here used this library for concurrency in Python? Like, raise your hand. Oh, wow. No. Oh, yeah. No. I didn't mean Async IO. I meant this one. Has anyone used Async core? No? No? That's unfortunate. Like, I'm not making this up. This is a real library that existed in the language like ages ago, but no one's using it. And my guess is that it was unusual. So much so that in September 2012, there was somebody in the community that wrote a suggestion, a strong suggestion, to make a radical change to it. And it titled, Included Batteries Then Fit. And it wouldn't have mattered if Guido hadn't seen it. Like, at that time, Guido was working on the Google App Engine, on the library on Python that uses Google App Engine. And he was doing a lot of async stuff for it. And he had faith that Python has evolved as a language as to produce a good way to address this problem. And so he opened his laptop, and he started the folder called Tulip. My name is Álvaro Durán, and this is Codename Tulip and the making of async. My goal today is to show you the making of the semantics of concurrency in Python, and to help you understand the design strategies underneath it. So pause for a moment to think about how you get coffee at Starbucks. So if you get to the counter, you can choose to buy products that you can get right away, like cookies or a sandwich. And you can get products that you need to wait for, namely, obviously, coffee. So a cashier will take your order, and if you want coffee with it, he will mark up a cup with the specifics of the order, and she will place it into a cup. And then a barista eventually will pick up that cup, and with the specifics written on it, she will deliver, and she will give that copy to you. The key fact is that the cashier, by then, she will have moved on to attend a new customer. So that's concurrency in a nutshell. It's a strategy for doing multiple things at the same time. Like, can you see that there's two queues of people, like two rows? Queuing is what decouples the baristas from the cashier. It doesn't make things any faster, but at peak times, what this allows is to sell more coffee. The cashier will be very inefficient if, after attending the order, she will go, then switch to get the coffee, and then get back and pay, and the whole thing. It will be very inefficient. It's much better if we decouple these two roles so that people in the queue don't get frustrated and leave. And even though this strategy will be absurd, obviously, for Starbucks, sorry, it's very normal to write software in this paradigm. In 2010, like 2 years before this async core suggestion, Ryan Dahl had introduced this new project of him called Node.js. And he claimed that software engineers were doing I.O. wrong. He meant, what we mean by I.O., it's, in a nutshell, is when computer communicates with the outside. And it's scare quotes outside because it can mean different things. But since CPU cycles are correlated to response time, it is as if you had devices that took seconds to answer back, and you had devices that answer like years in comparison. There's this divide between these two stuff. right? So in order to get information from devices at the button, the program blocks because it has to wait idling in order to get the data back. And to get information from the device at the top, the program more or less gets them almost immediately, and it doesn't block. So the key stuff is that modern programming languages like Python do not acknowledge this divide. Languages are all about metaphors, and the metaphor for accessing the outside is incomplete in Python. What Ryan Dahl was getting at is that JavaScript, in his case, and Python generally as well, didn't have a semantics for concurrency, a consistent way to write software that does something else while waiting for a blocking I/O operation. It is easy to forget how Python constrains and also guides the way in which engineers write software. So consider how simply a semicolon expresses ordering. Like you don't get to execute readline until the open has finished. Or consider how a return statement allows functions to send value into the void only to be catched by Python and passed along with the control flow to whomever called that function. Exception handling builds on top of that functionality to provide a systematic way to unwind callers and callees if something goes wrong. And context managers build on top of that to give us an easy way to pin down the resources, such as reading a file, within the dynamic lifetime of the functions that get called while the file is open. Unless you are a beginner, these features of Python are completely working in camouflage. You don't get to think too much about them. And in fact, unless you write in a thesis, you don't consider all the alternative ways in which things could have been differently, or that any stuff was at some point in time, it was a bit controversial and subject to debate until what used to be commonplace was ultimately considered harmful. Python specifically has been refined over more than 30 years and fits together to provide a powerful scaffolding for writing software. That is, until you try to do things concurrently. In that case, you're more or less on your own. Considering how concurrency is very much around us in real life, Python is lacking a little bit. It just pretends that things always happen one damn thing after another. And maybe I'm wrong. Maybe like lacking semantics wasn't a huge deal. Like nobody cares. Like for a long time, it just concerned people building operating systems and database engines. And these people were freaks. They will endure long learning curves associated with complex frameworks. Like nobody else really cares. And now everybody cares. Why? So the answer is Moore's law. For the past 50 years, software engineers have taken for granted the improvement of their program's performance, thanks to faster chips. Doing things concurrently, wasn't worth it. It just took a few years. You had the new hardware. It's just twice as fast on its own. You didn't have to do anything. But such a free lunch is now over. And our computational ambitions will now have to be satisfied with responsive and scalable software. So one quick win in terms of these concurrency stuff is to use threads. I'm pretty sure that someone has heard about threads at some point. Raise your hand if you're there. Yeah. Raise your hand if you think it's a good idea. Yeah. Yeah, I thought so. Threads are multiple instances of your program, like running under the supervision of the central schedule. However, the problem is that switching between threads is very costly. You have to go to the scheduler inside the operating system, and it's just costly. So if you want to handle things like, 20,000 connections simultaneously, it's just too much. Even for powerful computers, it's just too much. So multi-threading in Starbucks will be as if employees were taking both the roles of cashiers and baristas at the same time. It works at a small scale, like small cafes do that all the time. There's a few people like doing everything. But at the scale of Starbucks, for instance, the context switching will be like too much. It will be as costly for humans as it is for computers. So switching between threads is a bad idea. What about not doing it? What about doing concurrency on top of a single thread? That's not unlike how operating systems do it. They execute on top of a single CPU that has no notion of multitasking, anything, it just runs. And if the orange arrows represent programs running on the CPU, then there are special instructions that are called traps that are being read by the CPU as suspend this program, get control back to the operating system. And then the operating system, what it does, it then resumes, decides which program execute next, gives control to it. So the next program will hit another trap, and then the operating system will do the same, and so on and so forth. Like given this flow, these run, trap, run, trap, run, trap, run, trap dynamic, right? This design allows engineers to programmatically decide on which places the program is going to voluntarily yield control to the OS. It's like a relay race. The operating system and the programmers, they take in turns with the baton of control. And they're always passing it to or receiving it from the operating system. This strategy allows a single CPU to run on only one program at a time. And yet, it conspires with the operating system to give us the illusion that the computer is running on top of hundreds of chips. Making the async in Python is a similar strategy. We're going to create a system that runs a single thread of execution, just like a CPU, but in such a way that coroutines take turns to support concurrency. And what do I mean by coroutines? Like, what's coroutine? I don't really know. Like, literally, I don't know. I've done research about this. Everyone has their own definition of it. Like, it means different things to different people. It's one of those sins of computer science. But all of these definitions share a few themes that maybe could help us anchor these concepts. So first, coroutines are independent because they have their own internal state and control flow. They are switchable because they can voluntarily pause and they can be resumed. And they are call stacks in the sense that they retain some memory of where they are paused, allowing other coroutines to communicate with them bidirectionally. But for a long time, Python didn't have any concept of coroutines, the way that it has classes or functions. But the language allowed for something similar, that check a few of these themes so that they can be repurposed as Python's coroutines. I'm talking about generators. Generators are functions which, when called, don't return a value, but an object. And crucially, you can call next to it to obtain values from it. Because that's something iterators do. Most tutorials and generators are focused on these iterative aspect to it. So they are usually defined as list comprehensions that can be called lazily. But importantly, and that's something that iterators can do, generators can be paused because they are repeatedly giving control back to the caller via the yield keyword. That's why calling the F, calling next to F, give us the 6th Fibonacci number, even though we have called next G earlier. So internal functions with their own internal function control, which can be paused from the inside. That's like independent, and that's switchable. But there are also callbacks. We can communicate with the inside using the send method. But before we can use it, though, they need to be called next first. That's what we call priming the generator, so that execution advances to the yield statement, and only then we can start sending values to it. So in this case, this is an averager generator, and what we do is insert items into it, and what it pulls back is the average of all the items that have been running so far. Notice that the yield now appears on the right-hand side of the assignment operator. The average is what the generator gives to whoever is calling it, and the terms is whatever gets inside. Because Python is reading from right to left, the assignment hasn't happened at the point of the yield, and that's where the baton of control would change. But what if I want to chain more coroutines on top of another? Like, I wouldn't be able to do these, right? So if I call yield to it, it will return the value before the averager will be done. Like, will be just the first item in each case. So I just need a way to suspend the grouper until the averager has been done. And that's exactly what yield from does. For as long as the averager is running, what is going to happen is that whatever is sent by main is going to be passed to averager, and what is yield by averager is going to be passed to main, while grouper is suspended. And one last trick. I just said that we need to prime the generator before using it. So if you're familiar with decorators, you quickly realize that that's something that decorator can deal with. But not only I can get it primed, what I can also get is, with the appropriate naming, I can flag it as a coroutine and highlight this intended behavior. And that's it. You got decorators, they are coroutines, and you have the yield from, so you can chain them. That's everything Guido needed to build Project Tulip, which eventually came Async.io. And yeah, most talk will go now to build our concurrent web service. But as I was diving deep into these decorators, keywords, fancy tricks, I felt more like the guy in Jurassic Park. Like, we were preoccupied with whether we could. We didn't stop with we should have done this. Was this a good idea? Was Async.io a good idea to begin with? Because it's confusing. If I'm having a bad day, nothing, and absolutely nothing, stops me from mixing and matching generators instead as iterators. Like, I will be using one when I'm supposed to be using the other. And like, if I'm having a bad day, that's bad. But second, I can introduce subtle bugs into it, because there's nothing signaling the language that it's a coroutine. Just removing the yield from it will mean that it's suddenly a normal function, and none of these next send mechanism will work anymore, and that will wreak havoc. But also it's limiting, and because that's as far as I can go with coroutines. Class have dunder methods, metaprogramming. There's tooling that expert engineers can use to manipulate and exert their will into their computer, and generators have none of them. The history of generator-based coroutines is the history of Guido's reluctance towards adding new keywords into the language. It's like adding keywords is like inventing a new piece for a game board. It's radical and it's backwards and compatible, so it's understandable. He was wary of it. And from the Python Tulip Google group, it transpires that he just didn't see good enough reasons to invent new syntax. And what he did was repurpose the yield word and the from word and combined it into something new. It's more or less like how human language evolved over time. So it's not that radical. So what prompted this was that the async core wasn't like doing its own thing. So Guido was aware of the problem, and he looked to the guys around and he asked, "What do you need?" And the developer of Twister, the developer of Tornado, the developer of G-Event, they were all trying to create adapters to each other. So that was Guido's solution. He created Async.io as the one event loop to rule them all. But that's the view from the perspective of framework builders. The view from the end user is quite different. They seldom combine Twisted with Tornado, much like web developers don't combine Django with Flask. Guido thought that community needed interoperability, but async frameworks implementers were just trying to eat at each other's lunch. There wasn't a community need. What implementers were in need was interoperability, but end users needed an API. And you can look at the execution of a stack of layers that communicate with one another. But that's not unlike an operating system works, right? Python runs to C, and then C has system calls, and that's what gets introduced into the kernel mode, and then it pulls back. It's roughly the similar idea. And so, separating coroutines from the generators that implement it, it's like separating the user mode functions from the kernel that executes them. So what am I saying? Am I saying that Guido is wrong? That in refusing the painful job of adding a new syntax, he enticed the whole community of engineers to treat his hacky workarounds as a Python gospel? No, I think Guido is right. And that's compatible with thinking that using generator-based coroutines should be considered harmful. In making the async, Guido paved the way to a new syntax. It reshaped the semantics for concurrency in Python. Taking the shortcut of just adding the syntax will be corrosive to the language, as any other taking the shortcuts will do. But because of this reshaping, Async.io is probably the best solution. It's probably not the best solution for concurrency anymore. It supports both the generator-based coroutines that I've just described, and also supports the new syntax. But they are these both supporting one another. It needs to make trade-offs all the time, and that means that Async.io is dying of a weirdest illness of all: success. Other libraries, such as Trio, have embraced the async-await syntax, and they've ditched the generator-based coroutines, so much so that you can't use them. You can't use generator-based coroutines on Trio. And that allows for innovations that Async.io has tried to backboard, but not successfully. In Trio, you can use context managers. That's something that you can't do in Async.io, like decide when something is asynchronous and when that asynchronously ends within a synchronous flow. So I could be talking about these a lot of time, but as you can see, he's already flagging. If you're looking for something cool and insane to do with your free time, async is like my top thing. It's like Alice in the rabbit hole. There's always a door. There's always a new door to be open. And my colleague Jan is giving a 3-hour workshop tomorrow where he's going to build an async framework from scratch. So that means that you're going to have 3 hours to explore this topic in much more detail. But that's it for me. And of course, if you have any questions, you can contact me via email, via Twitter, or via LinkedIn. And I look forward to coming to PyCon ZZ on many occasions in the future. Enjoy the rest of your day.
Thank you, Álvaro. Do we have any questions from the audience? There's a little off-topic one. What software did you use for the presentation?
Keynote.
Keynote. Okay. Any on-topic questions? So are there any other libraries we should explore other than Trio?
So Trio was born out of a necessity that Dave Beasley, who's the authority on generators, he realized that this was problematic. So he invented a library called Curio, and it was a toy project. As of now, I think it's no longer maintained. So there's Curios there. Trio is also there. I'm probably missing, but there must be some other libraries out there that support these whole thing. It's just a matter of time that one of them is going to prevail, in my opinion.
And since we have these different libraries like Curio and Trio and Async.io, aren't we back in the same situations like with Twisted and all the other frameworks before, or what's better?
Yeah, so it's really interesting that you're asking this question. So when Guido was introducing Async.io, he addressed these very problems with this XKCD comic where he's like, oh, we have 14 different standards. We need that one standard to rule them all. And then we got 15 standards, right? He was addressing these half jokingly, and honestly, when I was watching it, I couldn't say that he solved it. So yeah, we have now 15 standards apparently.
And what do you think about task group from Async.io?
Yeah, so task group works similarly to what I've described with the nursery pattern. There's this context manager. It's the same. It's roughly the same idea. It's actually try to copy paste what Trio did into Async.io. My experience with it hasn't been as clear and as natural as Trio, honestly.
Yeah, I guess that's the problem with backwards compatibility. Do we have any more questions? There's one.
Hi, do you have experience with IOHTTP or other HTTP async framework for Python?
Come again, sorry?
IOHTTP, like HTTP framework with async.
Yes, so AO HTTP is that what you mean? So that's a library that is built on top of Async.io. Something that's really curious to me is that there's a few projects that what they're doing is to build a framework on top of all these standards. So there's this AnyIO, which is a library that what it does is allows you to use the same syntax or the same private language to use both Trio and Async.io. Curiously enough, that's what Starlet use in the background to handle all these. So AIO HTTP, it's just one of them. It's just specific to Async.io. If you want to try something else, maybe this AnyIO is what you're looking after.
Thank you. Any more questions? Going once, going twice, and all of the other ones will be off the record. Thank you, Álvaro.